So we've talked about the fundamental theorem of calculus part 1, and now it's time to talk about the fundamental theorem of calculus part 2. Now these parts are related. Part 2, a little more mathy in a way, but basically we start off this part 2, if you will, of this theorem with the following function. I want to look at this function. You've maybe never seen a function quite like this, but now that we've talked about what the definite integral is, we can define such a function. So this is area, well, it will be an area function. We'll see accumulation function, but a is a function of x. So the input is x, and look where the input is. The input is our upper limit of integration in the definite integral going from 0 to x. And then we have a function, f of t, notice that we're integrating. It's the integrand, and we have our dt. So notice here, you've got an x, and then why are we changing the variable to t? We don't want to have the variable of our integration be x. That would be too confusing because x is one of our limits of integration. And so we have to choose a different variable than this x. And so t is just our integration variable, our dummy variable, if you will. Okay. So let's just interpret this and see. I've mentioned already that this is an area function, and let's see why. If this is the graph of the function f, you know, maybe this is kind of like a cosine function, it looks like, maybe, or some type, but whatever it is, let's describe some values. What would a of 0 be? Right? That would be the integral from 0 to 0 of f of t dt. Well, obviously, that is going to be 0, right, when the limits are the same. We can think about this again in terms of the fundamental theorem of calculus part 1, that this would be equal to what? The antiderivative, let's say the antiderivative of little f is big F, evaluated at the upper limit, minus the evaluation of the antiderivative at the lower limit, right? And again, where f, capital F prime, would be equal to little f, right? That's the fundamental theorem of calculus part 1. So, but you can see, right, if x is equal to 0, I'd have f of 0 minus f of 0, which is just 0. Does that make sense? Now, what about a of 2? Now, I plug in 2 here, and I get the integral from 0 to 2. Well, the integral from 0 to 2, let's look here, from 0 to 2, f, notice, is above the x-axis. So this area, and we can, you know, estimate this area. I don't know, maybe it's 2, something like that. But one thing I want you to know is it's some positive quantity, right? So this area that I've shaded in is going to be equal to a of 2. So I'm just going to write down here some positive quantity, right? Whatever that area is, that's the value of a of 2. Okay. And then I say, what's a of 4? Well, that's the integral from 0 to 4. Now, going from 0 all the way to 4, we're going to sort of accumulate, if you will, this area that we already have. But then from 2 to 4, we're going to accumulate area. But what do you note about that? From 2 to 4, what's going to happen? Well, this, let me shade in this area between the x-axis and our function, right? That's going to come in as what type of area? It's negative area, right? It's going to be some negative area. And again, that's because the functional values are negative on the interval from 2 to 4, right, when we define our definite integral. So what do you note? From 0 to 4, this area that I've shaded in red and this area here that's green, those areas appear to be symmetric to be equal areas, but this one is positive, that area, and this one's negative, that area. That's how the integral will evaluate this. And so basically what will happen when we combine these two numbers, this positive number and this negative number, we're going to get back to 0 again. All right. What about a of 6? Well, a of 6 now goes all the way from, what, 0 to 6 of the function f of t. So I'm going to integrate all the way from 0 to 6 now. Well, I'm going to have everything up to 4, which we know is 0, but then I'm going to accumulate everything from 4 to 6, which again, the function f is below the x-axis, so I'm getting, again, this negative area here. And so this and this is 0, and then so this is going to be some negative number, so I know a of 6 is some negative number. And finally, what's a of 8 going to be? I'm going to go all the way from 0 all the way up to 8, right? And from 6 to 8 again, we're back to being above the x-axis, so positive area. So by symmetry, it looks like these two positive areas and these two negative areas will cancel each other out, and we're back to 0. So you kind of see what's happening. We're accumulating area, and I say accumulating signed area, right? So the function little f that we're integrating is above the x-axis, we're accumulating positive area, and then if we go below the x-axis, we're accumulating quote-unquote negative area. So that's exactly what I want you to observe, that a of x that we've defined is the area under the graph of the function f of t from 0 to x. So we can think of this integral as an accumulation function. So we call this the area function or accumulation area function of the function f. If we have a lower limit of a, our lower limit here was 0, but I could have started at any value. I could have started at 1 or 2 or whatever. And so some arbitrary fixed value a. This represents the signed area under the graph of the function f from a to x. Okay, from a to x. Okay, let's play around with this a little bit. Let's look at this function. This is accumulation function, right? A this time is 1, right? From a to x, from 1 to x. And now you say, what's this u? Well, just using a different variable than x. Okay, usually we can use t. Here I'm using u. You cannot use x here. This can't be the integral from 1 to x, x cubed dx. That will not work, right? Well, this we can find a formula for this function, because this function now u cubed, I can find the antiderivative, right? So I can use the fundamental theorem of calculus part 1 to evaluate this, right? So this will be what? What's the antiderivative of u cubed? That's 1/4 u to the 4th, right? Just the power rule. And we're evaluating that at an upper limit of x and a lower limit of 1, right? So I replace x with, u with x, get 1/4 x to the 4th, minus 1/4 u, 1 to the 4th is 1, I get 1/4. Right? There is the function. A of x can be written this way, okay? And this, what will this give us? This will give us the area under the function u cubed. So if I were to graph u cubed, do you remember what u cubed looks like? The cubic function kind of looks like this. Right? U cubed. And so we're going from 1, right? So here's 1, which gives me a height of what, 1, right? And so, you know, let's say some arbitrary value x bigger than 1, then what are we getting? This formula will give me this area right under the curve. In fact, this area from 1 to x is equal to 1/4 x to the 4th minus 1/4. So if x is, say, 2, I can plug in 2 and I get 2 to the 4th is 16. I get 1/4 of 16 is 4 minus 1/4. That's 3.75. So if x is 2, that area is 3.75. So that's a pretty neat thing. We can get a formula for that area that we get. Now, let's go ahead and find a prime of x. Well, that's pretty easy. I can take the derivative, I hope. Pretty easy. If this is a of x here, therefore a prime of x is what? I've got the derivative of this first term. 1/4 is a constant multiple. Take the derivative of x to the 4th, that's 4x cubed, minus the derivative of 1/4, that's a constant of 0. And of course, 1/4 times 4 is 1, and so I hope everyone easily determines that this is x cubed. Okay. But here's an interesting thing, right? If you observe where we started from, a of x was defined to be the integral from 1 to x of u cubed, right? We integrated and we got this as our area function. We took the derivative, we got back to what? The x cubed, right? U cubed, x cubed. Now it's different variables, right? But it's really essentially the same function. So integrating and then differentiating, we're going to see are sort of inverse operations. They cancel each other out. I integrate and then differentiate. I'm right back where I started from. And this is the idea behind the fundamental theorem of calculus part 2. And that is, if I have an area function like this, if I take the derivative with respect to x to find a prime of x, it's pretty darn easy, right? If I want the derivative with respect to x of this function, I could go through and integrate and find that area function, and then take the derivative. But sometimes we'll see we're unable to do that, okay? Either we're not prepared right yet to be able to find the antiderivative of the given function, or the antiderivative doesn't even exist. You can't find it. It's impossible. Then what do? You can't get this function. Well, we don't need it because we know from this example, at least it appears to be, and we're going to prove it, that the derivative of this function of a prime of x will clearly just be what? Replace the u with an x, it's going to be x cubed. The original integrand, just replacing the variable. And let's just prove that. So that is indeed the fundamental theorem of calculus part 2. And it says that if the function f is continuous on an open interval I about a, the derivative with respect to x of this accumulation function, a to x, and notice the different dummy variable here than x, anything different than x, f of t dt, is just f of x. Right? And the proof of that we can use is basically what we did in the example, so we'll just prove it in general. So if I take the derivative with respect to x of the integral from a to x f of t dt, right, then I'll go ahead inside the brackets, I'll just use the fundamental theorem of calculus part 1, which says the antiderivative of little f. So let's let, again, big F prime be little f. Then this is just evaluate the antiderivative at the upper limit, right, minus the antiderivative lower limit, right? That's the fundamental theorem of calculus part 1. Okay, so now we take the derivative with respect to x of this expression. Well, it's just the difference of two things. What's the derivative with respect to x of capital F? Well, we know f prime is little f, so the derivative of capital F of x is little f of x. What's the derivative of f of a? Is that f prime, little f of a? No. F of a is what? A fixed value. A is a constant. F of a is a constant. This is a constant, right? This is a constant. There's no variable here. What's the derivative of any constant? 0, right? And so you see we indeed get f of x like we have here. So the derivative with respect to x of that is indeed f of x. So take a look at this example here. If I wanted to find the derivative of this function g of x, right, then we could say, all right, let's use the fundamental theorem of calculus part 1 and find the antiderivative of the square root of t squared plus 1. But we don't have the tools to do that right now. We don't know what the antiderivative is, what function whose derivative is this. Okay? And so let's use what we learned up here though, right? So what's this say? This says g prime of x is going to be the derivative with respect to x of this stuff, the integral from 0 to x, square root of t squared plus 1 dt, right? And so matching this up with here, this right here is the f of t. Right? We could integrate that, and if we knew what the antiderivative of capital F was, like we did here, but then when we differentiate it, what's going to happen? We're going to get right back to that function, right? We get right back to f of x. And so the answer is just f of x, right, which is what? The square root of x squared plus 1. And that's it. That's it. That's easy, right? Not much to that. In fact, now I can find, if I wanted to, I can find g prime of 3. Obviously, by just plugging in, g prime of 3 is going to be the square root of 3 squared plus 1, which is the square root of 10. Right? So I can find that now. Okay, but there are some more challenging ones if these limits of integration are slightly modified to different values. How do we proceed? And so I'm going to look at that in the next video.